Hello AP Chem, this is Chapter 6, Thermochemistry. We're pages 210 to 248 out of the Zumdahl textbook, and this is Mr. Koker. So, Chapter 6, Thermochemistry. The thermo is for heat or energy. So we're looking at the impact of energy on chemistry. So let's talk a little bit about energy, the nature of energy. We know that there is a law of conservation of mass. There's also a law of conservation of energy that says that energy can be converted from one form to another, mechanical to electrical, nuclear to mechanical or electrical. Chemical energy can be turned into energy of motion. But even though energy can be converted from one form to another, it can never be created or destroyed in ordinary chemical or physical changes. I would say that nuclear reactions are a way of converting matter to energy and energy to matter, but in ordinary chemical or physical changes, we know that energy can change forms but is not created or destroyed. If we look at the two main forms of energy, potential and kinetic, potential is defined to be the energy of position, or in chemistry we could say the energy of composition, or the energy of bonds. So for chemicals it's usually the potential energy of the chemical bonds that we're talking about, and that could be the covalent and ionic bonds, it could be the intermolecular attractions like hydrogen bonding or London dispersion forces. Kinetic energy is the energy of motion. Kinetic energy is defined to be 1/2 mv squared. For chemicals, we're looking at the kinetic energy as being associated with the temperature of the molecules. The motion of the molecules is where the kinetic energy comes into play in chemistry. So temperature is a measure of average kinetic energy of the particles in a sample. Heat is the transfer of energy from a hot to a cold objects. When you have high temperature, if you look at the diagram in the lower left, when you have high temperature and it is close to low temperature, the collisions between the high temperature molecules and the low temperature molecules is going to transfer energy through those collisions away from the high temperature molecules to the low temperature molecules until both are the same temperature. We say that is thermal equilibrium, when both samples in touching each other are at the same temperature. So we're going to see transfer of energy from high to low temperature. That transfer of energy, the number of joules of energy transferred in that way, is called heat. So having a high temperature means having a high average kinetic energy. Having a low temperature means having a low average kinetic energy. When you put something hot next to something cold, heat travels from hot to cold in the form of the collisions that occur between the high temperature molecules and the low temperature molecules. There's also another form of energy known as work. Work we've seen as a force acting over a distance. So molecules do exert forces. When those forces are able to push something, that's doing work. And so that is another way that chemicals can transfer energy, is in the form of work. Now, whether the energy is converted to work or to heat or to some other kind of energy can depend on the pathway of the chemical or physical process that you're doing. Pathway becomes important when we define something called a state function. A state function or a state property is a property that does not depend on the pathway of the process. For example, non-chemistry example, if you drive from Chicago to Denver, your change in elevation from Chicago to Denver is a state function. The difference in elevation from Chicago to Denver just depends on the elevation in Chicago and the elevation in Denver. However, the distance you travel to get from Chicago to Denver depends very much so on the path that you take. So the distance traveled from Chicago to Denver is not a state function, but the change in elevation from Chicago to Denver is. So energy, or internal energy, is a state function, but heat and work are not. For example, you could lose 50 joules, and it could be all heat or it could be all work. It could be 25 joules of heat lost and 25 joules of work lost. Depending on the pathway that you take to go from one state to another, heat and work could be different. We've already talked about heat transferring from hot to cold, and it's due to the collisions between the molecules. Those with more kinetic energy will give kinetic energy to those with less, and that's just simply transferring heat from hot to cold. Chemical energy can go up in a system, we call that endothermic, or down in a system, we call that exothermic. Chemical energy depends on the strength of the bonds before and after a reaction. As you know, breaking bonds is endothermic and forming bonds is exothermic. So if you look at the amount of heat you put in to break the bonds and then subtract them or consider the amount of heat given off when bonds form, you can calculate the chemical energy as being either endothermic or exothermic. The first law of thermodynamics comes into play here. We'll look at the other two laws later when we get into thermodynamics, but the first law of thermodynamics simply says the energy of the universe is constant. We can change the form of energy, but energy can't be created or destroyed. The internal energy of a system is the sum of all the kinetic and potential energies of all the particles in a system, which is a very difficult concept to actually measure. So typically we measure only changes in internal energy, and we do that in the form of heat plus work. So delta E equals Q plus W is often how we define that. So when the heat is flowing into the system, we say Q is positive, and if heat is flowing out of the system, it's negative. If a system is doing work, then it's losing energy, so W would be negative. If a system is gaining, having work done on it, then W would be positive. So it's important to add Q plus W algebraically, keeping track of whether they are negative and positive. Now you might wonder, how does a system do work? So typically when we talk about work for a chemical, we look at the work done by a gas. We say that work is negative P delta V. When a gas uses pressure to change volume, for example, a gas pushes out and expands, delta V would be positive and work would be negative. So if a gas expands, it's doing work on the surroundings, assuming that there's a pressure that it's pushing against, P, and the change in volume is positive, and so in that particular case, work would be negative because the gas would be losing energy because it's using energy to push back the surroundings. So some excellent chances to practice this would be interactive examples 6.1 through 6.3. Real quick before we change slides, as it turns out, we always talk about into a system being a positive and out of a system being negative. So that is true for internal energy, it's true for heat, and it's true for work. So keep that in mind. You have a system, which is the chemicals that are undergoing the physical or chemical change, and then you have the surroundings, which are a place where energy can come from or go to. Now, measuring the energy of chemical reactions falls under the category of calorimetry. We have another state function besides internal energy called enthalpy, which is often what we're measuring when we measure the heat of a chemical reaction. Enthalpy goes by the symbol capital H. I've heard it called heat content as a way of trying to grasp what it actually is. It's defined thermodynamically as the internal energy plus the pressure of the system times the volume of the system. Now that's a bit of a confusing way of defining enthalpy, so let's look at it in terms of the change in enthalpy. What does it look like for a system to change enthalpy? If we start with the equation from the previous slide for first law of thermodynamics, delta E equals Q plus W, and we assume constant pressure, so then we can say delta E equals QP plus W. We can move W to the other side and get QP equals delta E minus W, replacing minus W with P delta V, because work equals negative P delta V. We get Q, the heat at constant pressure, equal to the change in the internal energy plus P delta V, which is work. Delta E plus work. So what we're really looking at here on the left side is that E plus PV, or delta E plus P delta V, is delta H, and delta H is Q at constant pressure. So in other words, the heat that flows out of a system or into a system when the system undergoes a change at constant pressure, which is typically what most of our systems are. If they're out in the open, they're at constant pressure. That is actually what the change in enthalpy is. So another way of looking at it is simply change in enthalpy is the heat that flows in or out of a system at constant pressure. We could define delta H, as we can any delta, as being the final minus the initial, or the enthalpy of the products minus the enthalpy of the reactants. Take a look at interactive example 6.4. So calorimetry is a science of measuring this heat. If you have a physical or change like melting ice, I believe we did the heat of fusion of molar heat of fusion of ice lab in Chem 1, or a chemical change, you can measure the amount of heat that's being transferred from or to the surroundings using calorimetry. Typically what we do here is we surround our chemicals with something like water, and we measure the change in temperature of the water. We say the water is the surroundings, and by measuring the change in temperature of the water, we're able to calculate the, based on the mass and the specific heat, we're able to calculate the energy that flows, say, into the water and out of the system, or out of the water and into the system. And so what we're doing, because of the conservation of energy, we're saying that any energy absorbed or given off by the water equals energy that is given off or absorbed by the system, and that's how we measure the heat of the heat change of the system. That means that we have to be aware of the heat capacity, which is the heat absorbed divided by the increase in temperature, so it's the number of joules per degree Celsius. If we say the specific heat capacity, what we're meaning is the heat absorbed per gram of material per degree Celsius, or joules per gram per degree Celsius. If we're talking about molar heat capacity, that would be the heat absorbed per mole per degree Celsius. So typically in chemistry, and especially in AP chemistry, we're going to use an instrument called a coffee cup calorimeter for measuring these heat changes. We can find enthalpy changes by using a coffee cup calorimeter, and what we're doing is we're measuring constant pressure changes, so that is enthalpy. Interactive example 6.5 is an example of using a coffee cup calorimeter. Constant volume calorimeters are a little more complex and expensive and harder to use, and more complex, but they are one instrument that chemists do sometimes use. Constant volume calorimeters, or bomb calorimeters, measure the internal energy change. So they don't just measure the um, the enthalpy change, they also measure the internal energy change. Because it is a constant volume calorimeter, there is no work. So since delta E equals Q plus W and there is no work, then delta E is simply the heat that's generated by the reaction as measured by the bomb calorimeter. Interactive example 6.6 shows you how to do bomb calorimeter problems. One very important law that we use in analyzing enthalpy change problems is something called Hess's law. Hess's law simply says that if you're going from a particular set of reactants to a particular set of products, you're going to have a change in enthalpy. It's either going to be endothermic or exothermic, and there's going to be heat that flows out or heat that flows in. But you can consider that change in enthalpy in going from one set of reactants to a set of products as being the same whether you do it in one step or in multiple steps. So just to illustrate this, we could think of the reaction as N2 plus 2O2 makes 2NO2. We measure the enthalpy change for that, and it's 68 kilojoules. And that would assume 1 mole of nitrogen and 2 moles of oxygen making 2 moles of NO2 would give off 68 kilojoules. Actually would absorb 68 kilojoules because it's positive 68. N2 plus O2 makes 2NO to make nitrogen monoxide instead. The delta H for that, we'll call it delta H2, is 180 kilojoules. If you then take the 2 NOs and add another O2 and make 2 NO2, by doing those two reactions, delta H2 and delta H3, you've basically done delta H1. If you add those two reactions together, you get the end result is that you've done N2 plus 2O2 makes 2 NO2s. Well, 2NO plus O2 makes 2 NO2s, delta H3 is negative 112 kilojoules. So if you add those two reactions, you get the reaction at the top. If you add the delta H's, 180 minus 112, you get the delta H above, 68. So it doesn't matter if you do it in two steps. The overall delta H, the sum of the two reactions, is the same as if you had only done it in one step. So this is kind of a new way of writing chemical equations. The left side looks fine, but we're also adding this delta H term out to the side. When we add an energy term to a chemical reaction, it now becomes something called a thermochemical equation. So we already know about chemical equations, but now we're adding in thermo to our chemical equations. We're adding in the delta H of the reaction, the enthalpy change of the reaction. Now, these thermochemical equations have a set of rules that you can use. It's very useful for analyzing these thermochemical equations. The first rule is if you reverse the reaction, if you flip the reactants and the products, the sign of the energy change simply changes sign. So if I were to write, for example, up above, instead of N2 plus 2O2 yields 2NO2, delta H1 equals 68 kilojoules. If I wrote 2NO2 yields N2 plus 2O2, then the delta H would be negative 68 kilojoules, be exothermic. Now, the amount of energy change is also proportional to the number of moles of chemicals reacting. When we write these reactions, such as N2 plus 2O2 yields 2NO2, delta H1 equals 68 kilojoules, what we're saying is 1 mole of N2 and 2 moles of O2 make 2 moles of NO2, and when that many moles react that way, the heat change is positive 68 kilojoules. Now, if you were to double the amount of chemicals, let's say make that 2N2 plus 4O2 yields 4NO2, by doing twice as much reaction, twice as much heat would flow, and so delta H1 would be 136 kilojoules in that case. So if you multiply a thermochemical equation, you multiply the energy change. So some things we can gain from this. We can add chemical reactions together and just add their heats together and get different chemical reactions. We can also flip reactions around as needed to get the chemical reactions aligned the way we want to be able to add them together to get the chemical reactions we want. If you flip a reaction, it simply changes sign. Interactive examples 6.7 and 6.8 let you practice adding reactions together to get new reactions. Now, with that in mind, Hess's law and the idea of adding reactions together to get the delta H's for other reactions, chemists want to find the delta H of various reactions, and one thing that might come to mind is maybe we could take a set of chemical reactions that we know the enthalpy changes for, and then by using that set we could combine them in various ways to make some different reaction that's not in our list, but simply we can take reactions we have in our list and add them up to make the reaction that we want. So with this in mind, chemists have developed a concept called Standard Enthalpies of Formation, or delta H naught F. I read the degree sign as a naught, kind of a letter zero there. So delta H naught sub F simply stands for the standard enthalpy of formation, which means what would be the change in enthalpy, what would be the heat that flows in or out that would accompany the forming of a mole of a compound from its elements, assuming all the substances are in their standard state, that the elements in the compound are all in their standard states. So enthalpies of formation are going to be in units like kilojoules per mole. It's the amount of heat that flows in or out of the system at constant pressure if you make a compound from its elements. These sets of enthalpies of formation could then help us by adding those reactions together. We could get other reactions, and I'll show you in a minute how that's actually done. First, though, let's define what a standard state is. A standard state, and the word standard is designated with that degree symbol, or I usually read it as naught. A standard state can be defined the following ways. If it's a gaseous substance, then the standard state would be to have that gas at 1 atmosphere and a temperature of 25 degrees Celsius. If it's a pure liquid or solid, it's quite simple. It's simply the pure liquid or the solid at 25 degrees Celsius. If it's a solution, that is our chemical, then we say that 1 molar concentration for that solution would be its standard state at 25 degrees Celsius. And then for an element, the standard state is the form of the element that is stable at 1 atmosphere and 25 degrees Celsius. For instance, for oxygen, that would be O2, not ozone, O3, because ozone isn't really stable at 1 atmosphere and 25 Celsius. Oxygen is. For carbon, it would be graphite, not diamond. Diamond is actually less stable than graphite as far as enthalpies of formation go. So one thing to remember is how standard enthalpies of formations are defined. It's forming a compound from its elements. That means the enthalpy of formation for an element would be assumed to be 0. So because if you make an element from an element, then you're not doing anything, and so there's no heat flow. So how do we use these standard enthalpies of formation? The picture down in the lower left sort of illustrates it. For the reaction CH4 gas plus 2O2 yields CO2 gas plus H2O gas. And I should interject here, it's very important for these reactions that we do designate the state, whether they are gas, liquid, or solid, because the same chemical at a different state has a different enthalpy content. Because bonds do form and break when things change state, at least intermolecular forces do, and that changes the enthalpy of the system. So it's important to designate when we're talking about the enthalpy change of a reaction what the actual states are, because with different liquid, solid, gas states, they would actually have different enthalpies of reaction. So the idea of using this enthalpy of formation to add reactions together and get new reactions, it goes as like this. If you have your reactants, in this case CH4 plus 2O2, you could take those reactions and convert them to all elements, and that would be carbon, hydrogen, and oxygen. So what that would actually be the reverse of a standard enthalpy of formation. If you think about enthalpy of formation, it's supposed to be making a compound from its elements. If you took the compounds that are the reactants and turn them into elements, you are simply doing the enthalpy of formation in reverse. You're unforming them. Then if you take, after you have converted the reactants to their elements, if you then take those elements and recombine them to make the products, now elements to products, that is actually the enthalpy of formation of the product compounds, in this case CO2 and water vapor. What you're really doing here is you're saying this reaction can be broken down into two reactions. One, which is a reverse enthalpy of formation, to take the compounds and the reactants and turn them into elements, and two, to take those elements and make compounds that are the products. So that means you should be able to take the enthalpies of formation of the reactants and the products and combine them in a way that gets you the enthalpy of the reaction. And that's simply what the equation to the right shows us how to do. Delta H of reaction equals delta H of formation of the products minus the reactants. Notice we're adding the products, but we're subtracting the reactants. We add the products because that reaction to make products is actually going in the right direction, elements to compounds. We subtract the reactants because we're flipping that reaction, which is compounds as reactants turning into elements. That's the reverse of an enthalpy of formation. Now, if all that complicated description didn't quite sink in and you want to ask me in class about that, I encourage you to do so, because it's kind of an elegant way of looking at the Hess's law, and it's simply saying that if we have the enthalpies of formation of a lot of different compounds, then any reaction involving those compounds, we can figure out what their enthalpies of those reactions are just by doing the algebra on it. You might wonder, where are these enthalpies of formation? There's actually a large number of them found in Appendix 4 in the back of your Zumdahl book. So I encourage you to look those up in the back and try some interactive examples, 6.9, 6.10, and 6.11. Okay, so we're just going to wrap this up quickly by talking about some examples of energy and energy use by our world and by the United States. If you look at this pie chart of energy use, you can see that fossil fuels still, even in the modern age, still dominate our energy use, with petroleum being the highest amount of energy, most of that used in transportation, natural gas being used mainly for heat, and then coal and some natural gas being used for electrical energy production. We just don't see a large part of the pie chart being these other forms of energy, but we are trying to increase politically and socially. We're trying to increase our use of other forms of energy to cut down on the amount of fossil fuels that we're using. For example, nuclear energy, biomass, which would include like ethanol and soy biodiesel, and burning wood in your home to heat your home is actually biomass. Hydroelectric is a very small percent. That's using hydroelectric dams. Wind is also another very small percent. Solar is another small percent. Geothermal, another small percent. So what we find is that the United States is still largely dependent on fossil fuels. And of course, fossil fuels cause a variety of air pollution, mainly in the form of nonmetal oxides. Of course, everybody always goes to carbon dioxide, which is causing the greenhouse effect, but there are also nitrogen oxides that form in car engines, because the heat in a car engine, the temperature of a car engine, can break the N2 triple bond and the O2 double bond and make nitrogen oxides. When I spent a summer in Los Angeles with my brother when I was in college, I went out there for a summer and stayed with him. And over the city of Los Angeles, you can actually see a red-brown haze, which is actually nitrogen dioxide in the atmosphere from all the cars driving and burning gasoline and making nitrogen oxides coming out their tailpipes. We also have a problem with sulfur oxides, especially if you burn sulfur coal. Sulfur oxides produce acid rain because they turn into sulfurous and sulfuric acid. So if you think about chemistry and the uses of energy, this is one of the major problems that chemistry hopes to solve in the upcoming years. And that is, how can we use energy smarter? How can we do a better job of our energy consumption? One thing that we have these new energy sources that chemistry is trying to develop and engineers are trying to develop to solve the problem of the energy needs going into the future. One is how are we going to burn energy? What energy sources are we going to use to burn in our homes for heat and also in our cars for transportation if petroleum and natural gas are someday if we someday run out of those. And one idea that's being worked on is something called a syngas, which is actually a combustible gas that can be made from coal. Another one is the idea of using electricity from other sources to make hydrogen and then burning hydrogen in vehicles. Of course, if you burned hydrogen in your car, hydrogen is explosive and it will burn, and you can design a car engine that burns hydrogen. If you do so, water is the product that's coming out of your tailpipe, and you're basically lowering your carbon footprint. Considering trying to search for more oil and gas that we can burn in our vehicles, one idea is once the liquid reserves of oil are used up, that we may go to some of the more difficult forms of oil to extract, and that would be oil trapped in rocks such as oil shale and kerogen. These are oil petroleum products that are trapped in between layers of shale and in porous rock. Kerogen is in porous rock. And extracting that can mean simply heating those rock sources up and forcing the liquid portion out of it. One area of energy use that is increasing in our gasoline and helping the economy of Champaign County is the use of ethanol from corn. Ethanol is made from fermenting sugars, and so cornstarch can be broken down into sugars, which can be made into ethanol. There's an ethanol plant in Gibson City that makes ethanol for mixing with gasoline. California is testing methanol as a source of methanol. Is I think it's usually called wood alcohol, so I would assume that it's made from wood. So there's a different bio fuel there. Soy-based biodiesel. Once again, you're using a product that local farmers are growing to make diesel for diesel tractors and diesel semi-trucks. Seed oils are something that the farmers and the chemists are working on, trying to get seed crops that can be processed into oils, and then maybe those oils could be burned for energy. Then you get various kinds of energy from plants or biomass, and the nice part about those is we can continue to grow those. and so fuels from plants are renewable.